Alrighty, so you should have in front of you the white foldable that has a whole bunch of graphs and boxes and kind of notes written on it. Let's start by folding it the way it should go. So you'll start up there at the top. I've drawn some diagrams. You're going to start with the printed stuff facing you, okay? You're going to fold it hamburger style so that it's in half, like this diagram. Then open it back up, like you see right here. You should have a little dotted line down the middle, a fold line, right? It's like your middle line. Then you're going to fold each side into that middle line, okay? So you've kind of created two shutters, as you see right here. Then, this is the tricky part, you should have these shutters, right? You're going to then fold it, with the shutters closed, you're going to fold the top part down, okay? And you're going to fold it until it looks visually like you've split it into two pieces, halfway there and halfway here, okay? When you open it back up, I didn't draw this one, it'll look like this, okay? From there, your goal is then to fold the bottom half up to meet that crease line. So then when you open it back up, you have three sections. You've created thirds, okay? Once you've done that, you're going to cut along these dotted lines. Another thing just to consider, I probably should have said this at the very beginning, is that you can just kind of look at the inside and see how you're supposed to fold it. I tried to put lines on there to help you figure out how that's supposed to go, but anywho. So if you want to pause the video until you are ready with your foldable, go for it. Scissors are in the back of the room on the bookshelf. Get yourself ready to go. All right, so at this point you can go ahead and title each of the flaps. They should be blank if you folded it correctly, and we will fill in the insides once you've got all the titles. I would pause it now, plug all this in. Alrighty, so let's start with the very top left flap, the one that says negative f of x, okay? What this is, we're going to put the transformation title, if you will, in the box every time. This is a reflection. Sorry, my board, you know, isn't pretty. There you go. Reflection over the x-axis. Okay, reflection over the x-axis. So if we were to sketch out the parent function here, just kind of do the best you can. When we're reflecting something across the x-axis, that's going to result in a graph that looks like this. You saw this most likely whenever you were doing Desmos, and you were looking at all of the different ways you could change the slider. When the a became negative, you saw that it flipped down, right? So what would go in this blank is that it changes the concavity of the graph. It becomes concave down. Okay, so anytime you see a negative on the outside of the function, that means it's going to flip down. And feel free to add any extra notes that you want to on each of these flaps. This foldable is going to be seriously important for you. Going to be a great resource. I'd strongly suggest that you put as much as possible in here that you need to truly understand each of these transformations. Okay, so again, negative on the outside is reflecting over the x. So let's talk about a negative on the inside. Flap to the right. This, I'm sure you could guess, is when you have a reflection over the y-axis, okay? Over the y. So if I was to draw my parent function here, and sorry about the board, if I was to reflect this across the y, going this way, well, it's not really going to create any sort of noticeable change. It's going to look very similar, right? It's going to be almost exactly the same because the axis, the y-axis, is its own line of symmetry. So this first bullet point says unnoticeable when the axis of symmetry is x equals 0, otherwise known as the y-axis, right? So when you reflect something across the y that's already symmetrical about the y, you're not really going to notice anything. It's going to look exactly the same. However, this is noticeable when the vertex is not at the origin. In other words, if it's not the x-axis. So let me draw you another graph here. If our graph was somewhere over here, okay, and we wanted to reflect that across the y, well, obviously, that's going to wind up over here, and look totally different, right? So just keep in mind that this kind of thing, there's a reason it wasn't on your exploration activity yesterday, because you don't really need it to understand the reflections. However, and because it doesn't always show up. However, I do just kind of want you to understand that when it's on the inside, when that negative is on the inside right here, that just means it's a reflection over the y. Okay? So now open the flap titled a times f of x. This is where you're multiplying the entire function by some value a. What this creates, this is kind of some new words here, is a vertical stretch, that's a stretch, or compression. Okay? Vertical stretch or compression. Now what you really have to consider here is thinking about a rubber band. Okay? Just your standard rubber band. If you hold that rubber band at the top and the bottom, and you try to stretch it, okay, so I'm going to draw this out here. Here's my rubber band. If I try to stretch it by pulling at the top and the bottom, that rubber band is going to become skinnier, right? It's going to look like this. Or if I hold it at the top and the bottom and I compress it by pushing in, that thing's going to become wider. This is essentially what we're doing to our parabola when we vertically stretch it or compress it, okay? So a vertical stretch is when it gets narrower. Okay, it gets narrower. This is when a is greater than 1. Now notice I put the absolute value of a. That's because if we have -4, for example, well, -4 is not greater than 1. However, we're not worried about the negative because the negative just tells us it's concave up. So we really just care about the 4, and 4 is greater than 1. So that's why we care about the absolute value, okay? So if the absolute value of whatever a is bigger than 1, that's going to stretch it and make it narrower. Okay, so let's kind of look at this on a graph. Here's our parent function, okay? Again, if I stretch it this way and this way, it's going to make it skinnier, just like a rubber band, okay? Let's talk about vertical compression. This is when it gets wider, okay? That's whenever we're going to push down vertically, and it's going to squish out, just like the rubber band in your mind, okay? This occurs when a, the absolute value of a, I should say, is between 0 and 1, okay? So an example of this would be like 1/2 f of x. That's going to make it wider, okay? And we've kind of already seen this, right? The narrower version, if I want an example of that, would be like 4 f of x. That's going to make it narrower. All right, so the flap right next door is f of bx. Okay, this is very similar. You saw on that exploration through that Google form and through that Google Doc that f of bx is very similar to a f of x. They both deal with being wider and narrower, except that bx never goes negative, right? So this is a horizontal stretch or compression, okay? And this is where things get crazy. This is where everything is backwards from what you would think. Okay? I even have to like look at my notes when I do these things because I forget it, because it's not common sense. So, when it is a horizontal stretch, that is when it actually gets wider. Okay? And again, you have to think about your rubber band here. Here's my rubber band, standard. Okay? If I'm going to stretch it horizontally, it is going to get wider. Yeah? However, again, if I take my standard rubber band and I compress it horizontally, it's going to get skinnier, okay? Which again, to me is backwards, but whatever. So the next one would be gets narrower, okay? And again, we've got values for this. On the last page, the stretches occurred when the number was bigger than 1, but now it's the opposite. The stretches occur when it's in between 0 and 1, like a fraction. Same with the horizontal compression. Okay, so if I was to do examples of these, this would maybe be like f of 4x. Okay, or if I was to do the top one, an example would be f of 0.2x, maybe. Okay, and again, we're not worried about the negative because the negative is a completely different thing that has to do with the reflection. So let's draw again. Let's draw the parent function here. okay? And let's talk about stretching it and all that. If I was to stretch horizontally, going like this, obviously it's going to get wider, okay? If I was to compress it horizontally, that means it's going to get skinnier. And ignore my shifting up and down here. That's just due to my pen not being able to match. That doesn't actually occur when you horizontally stretch or compress. Alrighty? So now, let's shift down to the bottom transformations. F of x minus c and f of x plus d. Both of these are actually the easiest ones, probably say the easiest for last. These both just have to do with translations, okay? And you also kind of discovered these as you went through. So f of x minus c is horizontally translated. Okay? Horizontally translated. In other words, shifted, right? Shifted is a big word you use in 7th grade. Horizontally shifted around. So if we were to do an example, and honestly it's easier to see an example. If I were to do the example of, let me do a different color. F of x minus 4, okay? If I look back at my original transformation up here, it says f of x minus c. Well, the minus that was there before is still there. That means that my c for this problem is 4. It's not negative 4, it is a 4 because the transformation started as a negative. Whereas if I were to do another example, okay, I'm going to do a different color, and I did f of x plus 3, for example, well, that means that my c here has to be negative 3. Because if the transformation originally starts out as minus, and all of a sudden it's a plus, that means it had to be minus minus to get that plus. Okay? So now, let's look at our examples here. It says if c is greater than 0. Well, that's that 4 we just showed, right? This c is greater than 0. Okay, when that occurs, you are going to move to the right. Okay? If c is less than 0, that's like that negative 3 there, that means you're going to move to the left. Okay? Honestly, I have no clue. Oh, I know what I was going to put. I was like, I don't know. It goes in these other bullet points. But I remember. If you can't remember really this whole weird positive negative thing I was just explaining, I just remember that if it's a plus sign, it's actually moving to the left, which is opposite of what we think. And if it's a minus sign, it's actually moving to the right, which again is opposite of what we think. Okay? So again, if I have my parent function here, it's going to be shifted over to the right, like this, or to the left, like this. Okay? Again, that's one of the easier ones, just moving left and right. Doesn't affect the width, doesn't affect the vertex, just shifts it left and right. Well, it does affect the vertex, I'm sorry, just doesn't shift it up and down. Alrighty, last one. This one, if you haven't already guessed, is when you vertically translate something. Okay, very similar to the other side, so this one's even easier. If d is greater than 0, then that means that you are shifting up. Okay? In other words, plus sign. If it's plus, it's up. Okay? If d is less than 0, you're shifting down. In other words, if it's a minus. And that is what you would expect, right? So you don't have to worry so much about if plus actually means minus and all that jazz. So let's look at some examples. If you have f of x plus 4, that means you do shift up 4, because d really is 4. Okay? If you, that's a d, I should probably make that clear. Let's see if I can fix that a little bit. There we go. Okay, then the green, that's when we're shifting down. So let's say it's like m of x, remember these letters don't matter, m of x minus 8, okay? That means d really is negative 8, and it's been shifted down. Golly, there we go, d. Okay, so again, if I was to look at my parent function, shifting up, looks something like that. Is that better? And shifting down, it would be something like that. Okay? So that is just a real brief overview of the transformations. Like I said, you're going to want to keep this foldable very handy. I'll be referring to it in the next couple of days. your homework is going to require that you take an equation and tell me what happened to it, okay? So let me do one example of that and kind of talk you through how you can go back through your foldable to see it. I'm going to write on the right side because that side of my board is a little better. So if you have f of x equals negative 3 x plus 4 minus 8, for example, okay? This has a lot going on, a lot of extra numbers there, right, besides just the x. Oh, this should be squared. I'm so sorry. Squared. Again, if you think about what it should be originally, the parent function, it should just be f of x equals x squared, right? But we've added the 3, the negative, the 4, and the negative 8. A lot extra stuff there. So let's just break down what each thing means, okay? So let's start with just the negative. The negative alone means that it has been reflected over the x, okay? In other words, it's concave down, right? That's the first thing that's happened. Okay, let's talk about the 3. Just the 3 alone, that's on the outside of the function, right? It's not happening to the x on the inside, so it's on the outside, so it's like the a. That is either vertical stretch or compression. I'm going to go ahead and write vertical. I look back at my foldable. I see that it's a 3, so that it has to be bigger than 1, so it's a vertical stretch, right? And I remember that that means that it is getting narrower. Okay, so I know that it's narrower, I know that it's concave down, sorry. Okay, now look at the other things. I've got this plus 4 here. So think about what does plus 4 mean? Well, that's on the inside, so that's kind of like my C. I know that if it's plus, if I look at my notes, that actually means that I'm moving left. So this means I'm moving left 4. Okay? Last thing, we'll go back to red here, is this minus 8. Okay, well, minus 8, that's where my D is in my transformations, so my foldable. And I see that minus 8 means I'm moving down. So that means this thing has been shifted down 8. This actually tells you quite a bit about the function. The best part is this bottom portion right here. When we're talking about shifting up, left, down, right, et cetera, we're really just talking about the vertex. That's the one point that you know from the beginning started out as 0, 0, and has now been affected in these two ways. Okay, so if it was at 0, 0, and now it's moved left 4, well, that means negative 4, down 8, that means negative 8. I know what my new vertex is, which also means I know what my axis of symmetry is, right? Now, if I also know that it's concave down, I can kind of sketch this thing out pretty well. It's narrower than the parent function. I can get a pretty good idea of what this looks like, okay? So transformations are very important in helping you to learn about what a graph looks like strictly from an equation, okay? We're actually going to go more into this right here later. This is actually a special form called vertex form that we'll talk about pretty soon. Alrighty, so once you watch the video, you can go get the homework from the substitute. If you have any questions, you'll have to just wait until I get back. You can send me an email. I should be here after school.